look at the quotes, what Knut says is that he sort of compares, a programmer to an artist, and the program, which is the artifact that a programmer produces as an object of beauty, right? I mean, he also talks about how difficult it is to actually build software, and I mean, these are things that resonate with my own life experience as a programmer and a computer scientist. So I started out programming in Chennai. I joined Gindi Engineering College as an undergraduate in computer science in the late 80s. And this picture on the right is the building where I encountered my first ever computer. That was a mainframe, and I wrote Fortran programs. Using punch cards. What you had to do in those days was, in the evening I would go submit my program, punched in punch cards, and I would give it to the operator there. And the next morning, I would get the output in a printed manner. And if I made a mistake, then I had a 1 day turnaround time for every mistake that I could make in programming. So the world has changed significantly since then, but I still recall my experience with the computer very fondly. Um, so after my undergraduate degree in computer science, and I went to the US, I did my master's in computer science at the University of Virginia, Charlottesville. And then, then did my PhD also in computer science in the University of California at Berkeley. But interestingly, before doing my PhD, I worked as a programmer for about 5 years. I worked in the East Coast for some time. I worked in the Silicon Valley for some time, writing software for telecommunication as well as electronic design automation companies. And it really gave me a first-hand view of how difficult and challenging it is to write large programs, right? I mean, building large, reliable, robust software is, I think, one of the biggest intellectual challenges that I have ever faced. And then after my PhD, I joined Microsoft Research in Redmond in 1999, and I've been with them for the past 21 years or so. I moved to India in 2006, shortly after the lab in India got started. So that's sort of my story. And so why do I say that programming is an art, science, and engineering? Well, like Knut, my own experience is that well-designed programs engage with users like piece of art, right? If you write good software and you experience it as a user, you get an engagement much like you engage with a beautiful painting or a sculpture in a museum. But it's also in engineering, particularly when the programs become large, right? When you build something like an operating system or a browser or a complicated database management system, for example, it's really a collaboration with hundreds, sometimes thousands of programmers, and the size of the programs can be hundreds of thousands of lines of code, sometimes millions of lines of code, and that's very much an engineering exercise to make sure that the software you build is reliable, secure, performant, and so on. So it's very much an engineering discipline. And the reason why we say programming is a science is because every program is really a mathematical object. And questions about programs turn out to be questions about mathematics. And as an interesting tidbit, if you sort of think about an interesting question to ask is actually, can programs compute everything? Are there things that programs cannot compute? And that's a mathematical question. And the way one answers this question is first by observing that there are more functions than there are programs. So what do I mean by that? Suppose you take something like Java programs, and then there are an infinite number of Java programs. Suppose you just write down all the Java programs one after the other. So it turns out there is a countably infinite number of Java programs, but there are an uncountable number of functions, uncountably infinite number of functions, and those are both mathematical terms. So, but roughly what this means is that there are more functions than there are programs. So what this means is that there has to be functions for which there are no programs. There are functions which you cannot compute. And Alan Turing gave one such function. This function is a function. This function is much like a compiler. This function Q takes another program P as an input and some input X, and then it asks the question, when you run the program P on input X, will the program P, finish? Will it terminate and halt? It turns out that such a function Q is uncomputable. There's no computer program that you can write to actually take another computer program as input and then check whether that program will halt or crash or will it hang. Those are all interesting questions, right? I mean, if you download a phone app, you might want to know whether the phone app will ever crash or will it ever hang. It turns out that there is no other program that can do that automatically, right? So Manas, now you can, all the sound problems are gone, right? You can hear me now.
Yes, it's totally perfect now. It's perfect.
Okay, sounds good. Thank you. So as a consequence, right, what happens is that most questions about reliability of programs is uncomputable. So when you make a program, right, so you can't actually uh, determine ahead of time that this program won't crash. So in industry, what we do is we do testing. We actually check and run the program on as many scenarios as possible, and then examine and make sure that the performance of the program is satisfactory, and then we just ship it. But after we ship, right, the program might crash, on your machine, on your customer machine, and we routinely see that happening. And that's because of the fundamental mathematical limitations of what we can do and what we cannot do. And this actually, you might think is just a theoretical problem, but it's not a theoretical problem. I'll give you a few examples. This happened in 1996. They launched the Ariane 5 rocket, and it exploded in 40 seconds due to a software bug, which they couldn't discover in testing, and it actually manifested only when the rocket was launched. And then, in 40 seconds, they just lost, billions of dollars of taxpayer money was lost in this. I think this incident happened, if I remember right, in 2003. The entire northeast part of the United States, there was a power blackout, and this happened due to a computer bug. And the price tag for that was 6 to 10 billion dollars of money lost and inconvenience at a societal scale due to this. Um, and the fact that actually we can't reason about programs and build them robustly as we might like, is very much a very practical problem. And if you compare programming with other engineering disciplines, the other engineering disciplines, we have been doing them much longer, so we know how to build systems much more robustly. This is a stamp, commemorating, I think, an anniversary of the Brooklyn Bridge. I mean, currently the Brooklyn Bridge is still standing, right? It was built in 1883, and it has an uptime. The computer scientists call them as uptime, which is actually how long the bridge has been up. It's 137 years, right? And if you compare that with the uptime of your phone, I mean, I'm just put a question mark there. I don't know how long your phone runs before it crashes. I can tell you that it's certainly not 137 years. It's much, much shorter than that. And so an interesting question is actually, what is the difference between these two? Why is that, we understand, building a bridge much, much better, and then bridges, more often than not, don't fall down. They just stay up all the time. But when we build software, we do see actually that software is not robust as a bridge. And so why don't we have a mathematics for building correct software? I mean, partly because we do, but it's not as developed as the mathematics for building bridges. And there are several challenges. Um, there are two main challenges. One is actually we have to first. It's hard to describe what we want the program to do, which is actually what people call a specification. And it's hard to analyze programs automatically to check if they satisfy our requirements. Partly due to results like what I saw Turing showed. And so it's very hard to solve this problem. And there's a lot more research that is needed to get these programs to be solved much like the state of the art in actually building bridges or buildings. And despite these challenges, right, dramatic progress has been made from both scientific and pragmatic perspectives about how to build and verify software like mathematics, right? And I'll tell you a few stories about that. The first story that I'll talk about is our experience with Windows driver reliability. Many of you may know about these things called device drivers. Device drivers are pieces of software that connect your operating system to your devices. Like for example, right now, I'm sitting before a computer which has a keyboard, which has a mouse, and my headphone is connected to the computer via a USB port. Every one of them is a peripheral. And every one of those peripherals have a device driver that is managing the peripheral, and it is communicating and intermediating between the device and the operating system. And around the time I joined Microsoft in the late 90s, driver reliability was a huge issue. You might if you are using computers in the late 90s, you would have encountered screens like this. We used to call this as the blue screen of death. We call it BSOD. And a lot of times it turns out that these blue screens happen because of malfunctioning device drivers. And I think it's an interesting ecosystem because the drivers are written by hardware manufacturers, right? People who make peripherals, could be CRTs, your screens or your keyboards or a modem or a network card. They all write device drivers. And there is actually something called a driver programming model. And you could actually buy books like this written by Walter Roney that show you how the Windows driver model works. And so people read those books and they learn how to write a device driver, and then they write a driver for their peripheral, and Windows loads all of them. But it turns out that those drivers oftentimes are buggy. They have some problems. They don't always work right. And when those bugs are encountered, then it leads to those blue screens. So this turned out that since your computer has many drivers, even if each of those drivers have a small reliability issue, you can do some mathematics and calculate the reliability of the whole system. It turns out to be quite low. So it's actually imperative to make sure that the drivers have no bugs as far as interacting with the OS is concerned. And this is where actually we built a mathematically rigorous verification tool. We actually took all the usage rules about how people should write device drivers, how the driver should interact with the operating system, wrote them down mathematically, and then we built a mathematical tool that inspects the code and automatically check whether the code satisfies all those rules. And we do that automatically for device drivers. And this became a product called Static Driver Verifier. And Static Driver Verifier has now been used to check and remove bugs in device drivers for more than 10, 15 years now. It actually ships with every version of Windows. And it's a mathematical tool. And actually today, it is part of logo testing for drivers, which means that if you want to get a Windows certified driver seal, you have to pass the checks that are done by this device driver, by this verifier, and it has played a significant role in improving reliability, right? So that's an example of how these kinds of mathematical techniques can be used to improve reliability of real world software like Windows. And if you want to learn more about it, there is a CACM paper that my colleagues and I wrote in 2001. The title of the paper is "A Decade of Software Model Checking with SLAM," and you can here you can see a quote by Bill Gates, where he sort of brags about our company, talking about software verification, which is a holy grail of computer science, and now he talks about how we have now brought it to practice, and we are doing that in real world scenarios like driver verification, right? So that's an interesting story about verification. I will tell you a second story about design and how these rigorous methods can be used in design. And this story has to do with the design of the USB stack. So, my headphone is actually connected to my computer using a USB port. And you probably have, USB ports to connect your, cameras or, external hard drives or any other peripherals, right? Well, it turns out that around 2008, there was a new standard USB that came up. Now, before 2008, there used to be the USB 2.0 bus that looks like this small bus on the left, and the one that we are familiar with is actually called USB 3.0. That's much faster. And the older one used to be about 480 megabits per second, and this one's about 5 gigabits per second. And when this new bus standard came up, most operating system vendors, Windows and I'm sure Linux as well, we had to redesign the driver stack, for the device drivers that process this faster bus. And it turns out that designing software that functions at this speed, right? You have to process bits that are coming in at this speed is very, very hard. If you do that, you can make bugs, and then as a result, your computer can crash. So, together with Microsoft Research and Windows, what we did was that we came up with a formal design methodology by which we can design, the software that sits behind the USB port, which actually processes those, bits that come via the USB port, formally as state machines, and mathematically validate those state machines to make sure these state machines, never have bugs in them. And then we built a compiler that automatically compiles this formal model into code, and that's what runs, inside Windows 8, right? So here, you could actually search on the web for, building USB 3.0 support, and here are our colleagues in Windows, Randy Owl and Vivek Gupta, who used this mathematical methodology to draw the entire design of the USB driver, as using state diagrams, and then it was automatically compiled. And today, in Windows 10, Windows now runs on close to 1 billion computers in the world. It is this mathematically verified software that actually runs. If you're using Windows, right, you're probably using this code to listen to my talk right now, right? It's pretty amazing. And every time you plug a USB port, there's these mathematical models, and software that is generated from that is actually what is processing the bits that is coming on your computer. And if you want to learn more about that, you can actually read our PLDI 2013 paper written by me and my colleagues. The title of the paper is P, Safe Asynchronous Event-Driven Programming. I will tell you a third story, and then we will conclude. The third story is about the advent of machine learning, artificial intelligence, which is sort of very, very popular these days, and the impact that these developments are having on programming. So one of the things actually that our lab in Microsoft Research in India is doing is about thinking about how can AI and ML be used to improve programming, to improve the experience of programming. And it's the reason why this makes a lot of sense is that today everything is about data, right? Most software runs as services on the cloud. Right? These are all Microsoft services. Bing is our search engine. Office is a service. Windows is a service now. Azure is our cloud platform. All of these are services that run on our cloud, and which means that we can monitor everything that happens in our cloud. Like for example, when programmers write code and check them in, we monitor how many times they have checked in code. What have they done? What is the change of the code with respect to the previous version? When the program runs and maybe it crashes, we know why, how it crashed. What is the exact way in which it crashed? We can record that data. That's called telemetry. And we can monitor everything that's going on about this software, and we can collect huge amounts of data. And it's a very interesting question to see whether we can use artificial intelligence and machine learning on this data to improve the software development process itself, right? So my colleagues in Microsoft Research India are doing a research project called Sankey. And what Sankey does is that it collects data at every part of this software development process, not only during development, but during testing, during deployment, and post-deployment, and uses machine learning to answer very interesting questions like, for example, when a programmer checks in a piece of code, we can actually say how risky that check-in is, right? We can do that because we have past history, which says every time this piece of code was touched, we have past history which says actually something went wrong. So that we can give as a guidance to the programmer to say, oh, maybe we should test that code more because this piece of code has been risky in the past. Similarly, we can actually do things like, when something crashes, what you have to do is that you have to do something called root causing. You have to find out why that crash happened, and then you have to fix that bug, right? And the root causing process itself can be automated using machine learning. So, you can go to our webpage, you can search for, Project Sankey on your search engine, and you can access, many, conference papers that have been written. And this system is widely deployed and used inside Microsoft today, right? Another example I would give you is how programs integrally use machine learning. Like here's a very interesting program where I guess right now nobody is traveling, but before COVID, when everyone was traveling, if you were to take an airplane, you would get an email saying here is your departure time, arrival time, and software automatically extracts from this email this nice widget that can come to your mobile phone that you can now use to automatically check in. For example, go to the airline's website and do a check-in or print your boarding pass and so on. And it turns out that the software that you need to extract this kind of email that is about your ticket to a nice widget like that you can actually write that software in such a way, and you have to use machine learning and so on to build the software, so that if the format of the email changes, or a new airline comes up, right? Um, the software continues to function, without you having to rewrite the software, right? Because the format of this email might change. How can you make this extraction more robust? And it turns out that, as Manas was saying when he was introducing me, one of my research interests these days is in combining machine learning with with another research area called program synthesis. And by combining these, it turns out that we can actually write these extractions in such a way that they are robust to changes in the format of these systems. And if you want to learn more about that, you can go to my webpage, and together with my colleagues, you could actually look at our paper from PLDI 2019. So I'm coming close to the end of my talk. The next thing I want to show you is a demo of the use of artificial intelligence in programming, where this is a mind-blowing demo from OpenAI, from Sam Altman, about how you can just write comments in your code, and the AI can use those comments to automatically write code for you. So
I'm going to show what an OpenAI language model can do when applied to code generation. The model I'm using today was trained on code from thousands of open source GitHub repositories, using the same unsupervised techniques as our GPT models. Let's try it out. I'll start with a pretty basic Python task. I want to write a function to check whether or not a string is a palindrome. I'll start by writing the function signature and a quick comment string. And now I'll ask the model to generate the code that it thinks should come next. Great, the model got it right. But that was a pretty simple example. If I searched for is palindrome on Stack Overflow, I'm sure I'd find something similar. So let's step it up a bit. This time, I'll write a function that definitely wasn't in the training set. Let's return list indices for elements that are palindromes. And at least 7 characters. And let's see what code the model generates. Great, that looks right. And it even used the isPalindrome function from above. This time we can also rest assured that it didn't just copy some snippet from the training set. The model came up with a unique solution to a unique requirement. Let's step it up again. This time I'll write an order class close to items. I take system code in a class, properties of my order class. Now I'll write some methods to the order class. Let's start by writing a method to compute the total price. But let's add a twist. Let's apply a discount to items that are palindromes. Let's see what the model suggests. It helpfully writes a comment string for us. That's not quite right. It's applied to palindromes, not the whole word. Let's add a comment to clarify what I wanted. Compute the total price and return it. Apply discount to items whose names are palindromes. Let's try again. So far, so good. Great, that's much better. Actually, I wanted the default to be 20% off, not 80% off, but that's easy enough fix. There we go.
So I'll stop there. But it's a mind-blowing demo where he's just writing comments, and the system is actually automatically generating code, which in some sense implements those comments. This is my last slide. I want to conclude by talking about reimagining programming education. Because Plaksha is such an enlightened university with the goal of reimagining education. And in particular, I think we've been chatting with Manas, Vineet, and others in Plaksha about how we can reimagine the way art and science and engineering aspects of programming can be taught. And the opportunities are very clear. Using intelligent tutoring systems that watch student behavior, how can we actually have systems learn automatically how every student learns and provide them help in customized individual ways. Now, that's a very interesting opportunity. The other opportunity is to use the magic of software to connect students with not only their academic colleagues, but but as well as mentors from industry to enhance social connections and community learning while they are in the classroom. So these are some ideas that I think we're discussing. We can see, how these develop over time. And to summarize, right, I want to leave you with these three things. Hopefully, I have given you some perspectives about programming, both, as an art and a science, and how exciting and challenging a discipline it is. And the fact that programming is relatively a young discipline when compared to other forms of engineering, like civil engineering, where a lot more scientific work is needed to make programs robust, reliable, and predictable. It's very much work in progress. And the exciting new development in the block is the ubiquity of artificial intelligence and machine learning, and the challenges and opportunities it presents for programming as well as programming education. So I will just stop there and turn it over for questions. So maybe I should stop sharing my screen.
Yeah.
Yeah. And maybe turn on my video now, hopefully.
Yes. Good evening, everyone. Thank you for that wonderful talk, Dr. Rajamani. It was extremely interesting to hear about the history and how programming evolved through the various stories that you shared at Microsoft. My name is Kartika Kamath. I'm a Plaksha Tech Leaders Fellow alumnus now. I will be moderating the discussion along with Samrid, who is a part of the program team at Plaksha. We are now open to the questions from the audience. You can send in your questions by using the Q&A feature located in the menu options towards the bottom of your screen. It would be greatly appreciated if you could add your name and designation towards the end of the question. Let's get started with the question. We asked our audience to send us some questions before the talk, so we will be taking them up first. The first question is, yeah, it's an interesting question that what is the programming language of the future?
It's a very hard one. Typically, well, I mean, programming languages depend on what you want to do. I mean, there are many, many things you can write programs, right? Suppose you're writing, a database querying. Suppose you're querying a database. Today the most languages that are used to query are some variant of SQL, and that's what is used to actually query databases. If you want to write, client-side code, usually JavaScript is actually what is very popular today because that's what runs in your browser, and it's very ubiquitous. It actually can run on any platform. On the server side, I think Python is very popular these days. So those are things that are popular, but I would think that these things change with time, right? 5-10 years from now, these languages may not be the most popular ones, and we have seen that time and again. So one thing I would advise to students is to actually, while they learn programming and today's popular languages like JavaScript or Python or SQL, I think it's important to also step back and understand the foundations behind those languages, right? And because they're going to change. So in addition to learning programming, it is important to also learn the science of programming so that, as programming languages change, you can continue to learn them and build your career, and sometimes actually you may be the one that creates the next programming language as well.
Thanks, Dr. Rajamani, for that. So the next question we have is, what are the improvements in programming productivity that you forecast in the next 5 to 10 years, right?
So some of this is already happening. I think one thing that's becoming very clear is the use of intelligent assistants during programming, right? So, you saw, the OpenAI demo by Sam Altman, where, the programmer is editing and then an agent is watching and it is helping the programmer. And, I see this already happening, and I see more and more of this happening in the future. There'll be, it'll feel like somebody is pair programming with you, like this agent is watching you and helping you program. And such an agent will be very personalized because it will over time understand your own style of programming and it will be able to help you. And I think this will happen both during education and during professional programming. And my prediction is that you're going to see intelligent tutoring aids, which most universities will start using when they teach programming. They will be like a teacher that is sort of watching you and helping you learn programming. And then when you become a professional programmer, these things are going to still be there to assist you. And this is going to happen not only at the individual level, but at the team level. Like, what I told you about Sankey was one such. I mean, there's going to be intelligence that is going to monitor how the entire team is writing programs, and it's going to help them do their programming better. So essentially, right, the biggest revolution I see that's already happening, and it will happen more and more, is the use of intelligence in actually helping people write better programs.
So next question we have from Meghna. She's asking, can you please touch upon security and data privacy issues?
Yeah, I think both are very interesting topics. See, I think security is an interesting problem because I mean that nowadays I think everybody does everything online, particularly after COVID. Even you talk to a doctor online. You don't. You're just. I'm talking to you via my computer, and all your bank transactions are now being done online. We are using Paytm or whatever payment mechanism we have to make payments. As a result, right, the incentive for a hacker to hack into your computer and steal your money is actually quite large, right? And it happens all the time. I mean, you see in the news that be it Bitcoin or be it banks being hacked, a huge amount of money is actually being stolen by security bugs inside code. And so I think it's already an important discipline, and making your code secure so that hackers can hack into it is continues to be a very important problem. Now, privacy is slightly different because with privacy, what you're trying to do is that because of machine learning, most programs work by collecting data and then running AI and ML on that data. And what you want to make sure is that when you build those models, you respect the ownership and the privacy of the person to whom that data belongs, right? And this is a quite important thing because we may be able to collect data about patients, for example, during COVID, to sort of build machine learning models about how to treat COVID better, right? That seems like a societally important thing to do, but you don't want to do that while violating the privacy of the people who contribute that data, right? Because some people may not want everybody to know that they have COVID, right? Because there's huge harm that may actually be caused because of that. I mean, not just that, but other things as well. So I think as a result, right, privacy is something which is also not just technical. You have to think about policies about what is the social contract you're offering to the user of your software, because their data is being collected. What are you going to do with it? What are you allowed to do with it? What are you not allowed to do with it, right? And that's actually a conversation, a social conversation as well. So hopefully that gives you a sense. I mean, both very important topics. One in which there's going to be a lot more advancement and research in the coming years. Yeah.
That's helpful. Thanks, Dr. Rajamani. So we also have in the audience quite a few people who are just starting out to program, or some people who have been coding for a while. So the next question we have is from Vinay. He asks, software developers need to update their skills and knowledge of tools quite frequently, right? Sometimes it feels challenging. So he would like to know your thoughts on that, given that you mentioned that you initially used to work on punch cards, right? So how has the journey from there been to writing the programs these days?
Yeah, it's very interesting, right? Actually, I do verification research, and verification is about making sure that you write programs right the first time, right? It's not like you keep fixing them. I think, when I look back, I think partly it was because of my experience of writing punch cards, because when you write programs with punch cards, right, you get only one turn every day, right? And it's not like you can make a bug and then it takes a long time. I've seen programming environments change so much actually, and but what I would say is that the beauty of writing a program, right? Like you want to accomplish a task, and you're writing some code to accomplish that task, and that I think has not changed at all, If I look at, from the time I started my career, the fact that you have to do something and you accomplish that, and the intellectual energy that is needed to accomplish that, that hasn't changed at all. Whether you write that program in Fortran or whether you write in JavaScript or Python, that exercise is the same, right? So I don't actually, the intellectual energy of programming, I don't think will ever change, right? Maybe there'll be more tools. Maybe the AI will even suggest to you how to write code and so on, right? But the skills that you learn as a programmer are never going to go away, right? So.
So the next question is from Jugal. He just wants to understand this a little bit better, that when you talk about optimizing and debugging programming using AI, what sort of data has to be fed to the system and how can this be taken to scale? Also, what sort of algorithm or models are currently being used in this?
Yeah. So basically, right, the kinds of things that you can collect today are everything, ranging from version control. Today, your software is actually usually checked into a repository. Most of you may be using GitHub, that's what, or some version control like that. And so, every check-in you've done is actually already recorded there. So that information is there. And when you write tests, all of the tests is already there. And when you run a test, whether the test passes or fails, all of that data is there. And when a program actually runs at deployment time, it usually runs in the cloud these days. So you can monitor what the program is doing, how long the program is taking. When the program crashes, we can actually monitor how it crashed. So these are all the different kinds of data that we can collect. And that's what projects like Sankey collect. And then various kinds of machine learning models are built using that data to ascertain risks. For example, which parts of code are risky, which parts of the code are not risky, which tests are more important than others. Suppose you have like 100,000 tests, and if you only have 2 hours to run those tests, you can't run all those 100,000 tests, right? What are the most important tests to run? So those are the kinds of things. And actually, as I mentioned, also root causing, right? When something goes wrong, if your program is about 1 million lines long, where are you going to start reading the code to fix that bug that happened? And then we can use machine learning models to go from the symptom of the cause, the crash, to actual hypothesis about what the cause is, right? Those are examples of kind of things. I mean, another thing you can do actually use AI is to actually even connect people to each other. Like, for example, when you're programming, AI can tell you, hey, this colleague of yours is the most knowledgeable about this piece of code. So that if you want to talk to somebody, you please talk to this person. So, because in a large company, you wouldn't even know, who is working on what, right? So those are the different kinds of things that AI can be used for. Yeah.
Thanks for that, Dr. Rajamani. So we also have somebody asking a question about what they would like to teach their kids. So the question goes, how can programming be taught in an interesting way from the very beginning, the way we learn mathematics as a kid, right? Maybe he says, maybe I'm looking for an answer for the next generation. It could be applicable for his 4-year-old, and he would like to teach him from the age of, let's say, 6.
Yeah. So one thing actually we used to teach our kids is Scratch. You might try, Scratch from MIT. It's a sort of a kids programming language, where like a small script runs around your screen. It could look like a cat, and you write, visual programming to move that cat around. And I think a lot of kids have benefited. I think all over the world from Scratch. So that's something that you might check out. For a young kid, like 5th grade or younger, I think Scratch actually tends to work out pretty well. And if you are talking about older kids, um, I think the thing to do is to get them interested by doing things that they find exciting, right? These days you can get robots. Lego makes these robotic toys that you can actually program, and you can encourage them to build something that sort of picks up an object in one side and then puts them on the other side, and it's sort of, and how do you build that, right? Actually my kids are actually super excited when they see this Roomba vacuum cleaner that sort of goes around and vacuums our house. So one thing I would encourage actually parents is to actually teach kids using these sort of physical things that give a very visceral feel to kids about what you can do with automation. And as far as actually the question about mathematics is concerned, I really don't have an answer. I don't quite know how to teach the mathematics behind programming to young children. I'm really not sure. I'll think about that. And maybe, in a future occasion, I might give an answer, but I really don't know how to do that because it's very new. And even experienced programmers, it's hard to teach them, the mathematics behind programming. Yeah. And unless you, study in grad, a master's or a PhD program, those topics, they are not mature enough to become accessible to children yet. Yeah.
Yeah. So now we have this one person who has put in some rapid fire questions. So let me take that up. The first question is C versus Haskell.
So what about that? What's the question?
It's just what is your choice?
So again, actually, it depends on what you want to do, right? If you want to write low-level operating system code with very high performance, right, then you would use C. But it is a lot of effort to write programs in C. You can make many mistakes, right? But you'll get very high performance, right? But if you want to write code, whose correctness is easier, which doesn't have as many bugs, but maybe will run a little bit slower, then you could use Haskell, right? And then these two are very different ways of programming. When C is an imperative programming language, Haskell is a functional programming language, very different styles of programming. So the answer depends on what you want to do.
Yeah. So the second rapid fire is Python versus JavaScript.
Those are different, right? I mean, Python is usually more used for server side, and JavaScript is actually what you run on the browser. Again, actually, the answer is what do you want to do with it, right? It's like some of these questions look like Alice in the Wonderland, right? I think Alice asked the queen, where should I go? And the queen told her, it depends on where you want to go.
Right. Yeah. Bing versus Google, probably.
Let me not answer that.
Okay. So yeah, maybe the next question Samrit can take up.
Yeah. So somebody also wants to just go back to the GPT example that you gave, right? And the question is more about if AutoML for development is in place, what would be the future skills that we as humans will have to develop to work on the next level problem solving, right? And what should students be focused on learning skills considering the next 5 to 10 year horizon?
Yeah. See, it's unlikely that all of programming can be automated. I don't believe actually all of programming can be automated. I think the most that these kinds of tools can do is that they can provide assistance to help you, write programs. So I think actually, one advice I would give to students is again, in addition to learning Python or learning JavaScript, right, step back and understand the principles behind programming. That will actually make your skills more longer term. And instead of actually, don't be scared that actually this GPT-3 will, take away your job and it will write the code for you. And that's not what's going to happen, right? Use those skills to think about how you can be more productive on top of GPT-3, right? Embrace those tools because they are going to be there. And think about, how much value you can add over and above those tools, right? So that's my advice to you.
Okay, so given the paucity of time, we will be taking up the final question. We have quite a few high school students as well as educators attending the webinar today. So for the high school students, what career advice do you have as a professional for the students wanting to pursue their career in this field? And for the educators, according to you, what are the key steps that an educator needs to capture in order to teach programming as an art and science as well?
Yeah, very, very difficult question. I don't think there's one answer to this, right? But one thing I would actually tell high school students is that, what I have seen, I think, through, my career is that, computing is now actually become a tool, right? And, no matter what you do, whether you're a biologist or an economist, or you could be a doctor, I mean, it's like, you have to use a computer. You can't, every science is a data science these days, right? whether you're a physicist or an astronomer or an ecologist or an environmental biologist, right? A computer is now a tool, right? So I would think actually that, I think it's a tool much like any other tool, like mathematics, right? Just like you learn foundational mathematics, you have to learn computing, because no matter what you do, it's likely that computing is going to be a tool that's going to influence whatever discipline you study. And then actually follow your interest, right? Do what you like the most, right? And that way you enjoy what you do. That's what I would give as an advice to high school students. For educators, what I would do is that, particularly people teaching programming, I think, as educators, we have to understand that because programming is ubiquitous, we have to figure out how to teach programming to non-computer science majors, right? People with expertise in biology or social sciences even. Now, how can you make programming accessible to people who are not these, CS geeks? How do you do that? I think is a challenge. I think that's before us.
So thank you so much, Dr. Rajamani, for the talk and for taking all the questions. Right, I would really like to take this opportunity to express my gratitude to you, Dr. Rajamani, for taking out the time from your busy schedule and addressing all of us. It was really a pleasure to have you amongst us and acquire more knowledge about the art and science of programming. We would like to apologize to the audience for not being able to take up all the questions due to paucity of time. And before we close this session, I would request you, Dr. Rajamani, if you could share your closing remarks. I know you've already shared some thoughts for the educators and the high school students, but if you have some overall closing remarks that you would like us to leave, that you would like to leave us with as food for thought, please do help share your thoughts.
Yeah, I think what I would say is that, I hope I've actually shared excitement about programming as a career choice, and also the fact that so much needs to be done, right? It's a very young field. Everybody thinks that, oh, computers are everywhere, but computers have been around only for 60 years. Bridges have been around for thousands of years, right? So the computing revolution is already quite big, right? But it is still very early stages, right? So think about that, and in your lifetime, you will really see computing change, and you can be part of the change, and you can actually be the creators of that change. Right? That's I'll leave you with that. Yeah.
Thanks a lot, Dr. Rajamani. That was really inspiring. Once again, thank you for the engaging talk. I think I'll just take the liberty for speaking for the audience and say that we are all a lot more fascinated and inspired and motivated in this domain as we leave this talk. From everyone at Plaksha, I would like to thank the audience for tuning into Tech Talks today. This is the 7th talk we had in the series of conversations on how technology is empowering our changing world. Our next tech talk, titled Hacking Extinction, is on Friday, the August 7th. And our speaker will be Dr. Alex Dagan. Dr. Dagan is the CEO and co-founder of Conservation X Labs and innovator in residence and fellow at the Duke University and Arizona State University. Thanks a lot, everyone, once again, and stay safe.
Bye-bye. Yeah.
Thank you.